Hello students, how are you? I am fine. In the last class, we have discussed regarding the characteristic of the properties of halogens and the properties of hydrides of halogens. Today we are going to discuss regarding some important compounds of halogen, that oxides, oxoacids of halogens and their preparation, properties and uses. These are very important for our day-to-day life also. So let us discuss some important compounds. First, let us discuss the oxides. Oxides of halogen. If you see the formula of oxides of halogen, there are different types of oxides of halogens are possible, like this OF2, OCl2, ClO2, okay, then Cl2O3, Cl2O5, Cl2O7. These are some important oxides of halogen. You can change chlorine, you can replace chlorine by bromine, iodine also. These are some important compounds of oxides of mainly chlorine. These compounds is mainly, it has different structures. You see the structure of that OCl2, and this compound is very important for halogen, that fluorine, because fluorine produced in this compound, if you see the OF2, in OF2 that oxygen is +2 state. The oxidation state of oxygen, oxidation number of oxygen is +2. This is the only exceptional case that oxygen always carry -1 or -2, but when it combines with fluorine, then its oxidation state will be +2. This is exceptional, very important regarding the properties of oxygen, that sometimes question is being asked in your examination, that write the formula of a compound where the oxidation number of oxygen is +2, that is OF2, very important. And if you see the structure of OF2 or OCl2, both same, its structure will be like this: O here and F, and here also F. This one band set, this is also band set, having this electrons, and here regarding OCl2 also same, O, Cl and Cl, okay, having single bonds, and oxygen having how many? 4 electrons. So it will be like this, one lone pair remain. So this is band shape. And ClO2, if you see ClO2, this structure will be have a pi bond, sigma bond, sigma bond, and also chlorine remaining 4 electrons with oxygen, here 2 electrons with oxygen, 2 electrons with another oxygen, remaining 3 electrons on the chlorine atom. This is also bent set. Bent. This is also bent. Okay. Then, if you see the structure of Cl2O3, regarding Cl2O3, the structure will be, in this we can also do, here that one lone pair will remain here. Okay, so this is the structure of Cl2O3. And what is the structure of Cl2O5? Its structure is okay, having one lone pair. Here having one lone pair. So this is Cl2O5. Then Cl2O7, it is same. Okay, but here no lone pair remains on the chlorine atom because all are 2 plus 2 or 6, 1, 5. So this both have tetrahedral structure. This part is a tetrahedral and this part also tetrahedral. Tetrahedral and tetrahedral. 2 tetrahedral molecule joined. But this part, this one, this structure is pyramidal. This is also pyramidal shape, you can say. Not tetrahedral, 2 pyramidal molecules joined. Okay, this is part also pyramidal, 3 bond 1 lone pair. So these are some important structure of that oxides of halogens. Then if you see that regarding the reaction of halogens, you see halogen X2 plus water produce HX and HOX generally. X2 plus water produce HX and HOX. And this X2 plus water produce HX and HX is called hypohalous acid. This is called hypohalous acid, HOX. But only exception is fluorine. If fluorine react with water, it will produce mainly HF and oxygen. Exception. Fluorine with water produce HF and oxygen, but it cannot produce hypofluorous acid because hypofluorous acid HOF is unstable. That's why it dissociates, produce HF and oxygen. So this is a very important, but in all cases, chlorine, bromine, iodine always produce HOX, HOCl, HOBr, HOI like this. This is regarding the hypohalous acid. Similarly, very important thing is that halogen when reacts with sodium hydroxide in cold condition, in cold, it produces NaX plus NaXO plus water. This is very important reaction of this. But condition is cold. But same halogen when reacts with sodium hydroxide in presence of hot, when it is heated, the product is same NaX, but in place of NaXO, it is produced NaXO3. Instead of NaXO, it is produced NaXO3. But if you see, here charge is 0, here charge is -1, here charge is +1. Here charge is 0, here charge is -1, here charge is +3, +5. Here is plus 5. Plus 5 state. So here halogen, the oxidation number decreasing and increasing. Here decreasing and increasing. That's why here that same halogen in alkali, in cold and hot medium gets oxidized and reduced. So these two reactions, this is called disproportionate reaction. It is also called disproportionate reaction. Similarly, that if you see oxoacids of halogen, if you see the oxoacids of halogens, oxoacids of halogen, what are the oxoacids available? Generally HOX, HXO2, HXO3, HXO4. These four types of oxoacids are produced. This is called hypohalous, this is called halous, this is called halic, this is called porhalic. Halous, hypohalous, halous, halic and porhalic acids. These are the name of oxoacids. If you see their properties, here if you see here oxidation number of halogen is plus 1, here it will be plus 3, here it will be plus 5, here it is plus 7. Because the oxidation number of halogen is maximum 7, so it is mainly observed in perchloric acid. This is called porhalic acid. If you place chlorine, this is called perchloric acid. This is the oxidation number of halogen in different oxoacids. Then if you see the acidic character, the acidic character will be HXO4 is greater than, more acidic than HSO3, more acidic than HSO2, more acidic than HSO. Why? Because only cause is, if you see the oxidation number, it is plus 7, it is plus 5, plus 3 and plus 1. We know when oxidation number increases, the acidic character increases. That's why porhalic acid is more acidic than your halic acid, and here halous acid, and this is porhalous acid. So this is more acidic due to more number of oxygen, that is more oxidation number. If you change the halogen, that means HOF is more acidic than HCl. If HClO is more acidic than HOBr, you can write in the same way you can write HOF, HOCl, HOBr, then HOI. If you change the halogen, fluorine compound, oxoacids of fluorine is more acidic than chlorine, bromine, iodine due to more electronegativity. This is more electronegativity. Due to more electronegativity, HOF is more acidic. Then if you see regarding oxidizing character, oxidizing nature, This is acidic character. This is acidic nature. Acidic nature. This is also acidic character. Acidic comparison. Then oxidizing character, if you compare, oxidizing character will be HO. HXO4. HX4 is more oxidizing than HXO3, then HXO2, then HXO. Higher oxidation state, that's why easily reduced, so it can be acted as a stronger oxidizing agent. This is oxidizing nature. Oxidizing nature. More oxidation state, loss 7, so it is better oxidizing agent. Because highest oxidation state means only it can be reduced, so it is the strongest oxidizing agent compared to other. But if you take different halogen, the order is HBRO4 is more than HIO4 than HCl4. HBRO4 more oxidizing character than HIO4 than HCl4. This is oxidizing nature. This is regarding H. Okay. Then this is your oxidizing character, acidic character, and oxidation states of different oxoacids. What are the structures? If you see the structures of hypohalous acid will be HClO. This is HClO. HClO. Then HClO2. It will be OH. Then remaining this one SClO2. Okay. You can write also band structure having double bond, you can write 2 lone pair. Okay. Then HClO3 will be which okay, having 1 lone pair. HClO3. HClO4, it will be Cl, which having no lone pair. This is the structure of HClO3, that is hypochlorous acid, chlorous acid, chloric acid, and perchloric acid. Their structure. It is having here 2 lone pair remain. Your 1 lone pair, having no lone pair, 2 lone pair. This is the structure of your oxoacids, different oxoacids. Then next we will discuss interhalogen compounds. Different interhalogen compounds. Interhalogen compounds, that means it is the compounds in between halogens. What are these interhalogen compounds? X gas, it may be X gas 3, X gas 5, X gas 7. It depends upon the oxidation states. Here one is plus 1 state, another is minus 1 state. Here very important thing is that X gas should be smaller. X gas should be smaller. Very important point is that means smaller halogen. X gas should be smaller halogen and more electronegative and more electronegative. That means if you see the example for taking iodine, IF3, IF5, IF7. Here oxidation state is plus 1, plus 3, plus 5, plus 7. Already we have discussed halogen shows odd number of oxidation number, that is plus 1, plus 3, plus 5 and plus 7. Already you know, due to excitation of electron from lower paired subcell to higher energy subcell, then produce odd number of electrons. First one is having 1 electron, then 3 electron, 5 electron, 7 electron. That's why producing this. But very important thing is regarding the interhalogen compounds. Interhalogen compounds, short form I have written, interhalogen compounds are more reactive than halogen compounds. Than halogens. We can write halogens. Interhalogen compounds are more reactive than halogen because interhalogen compound has lower bond dissociation energy. You see the bond dissociation energy interhalogen compound is less because one is smaller, another is greater. For example, ICL is more reactive than I2. ICL is more reactive, that is reactivity. ICL is more reactive than I2 because the bond dissociation energy of ICL is less than I2 because one is smaller, another is larger. Due to this difference in size, the bond dissociation energy of ICL is lower than I2. That's why ICL is more reactive than I2. Similarly, if you see the structure of interhalogen compounds, suppose structure of IF3, if you see iodine, IF, it will be just a linear structure having 7 electrons, here 6 electrons, linear step. IF3 structure will be, it will be, you see, 3 halogen have 7 electrons, it has 7 electrons, then it share with 3, remaining 2 electrons. That means 2 pair. So 2 pair will be remain like this, then 3 fluorine will be in this pair. So this is T set. This is called T set. And hybridization is 3 and 2, 5. That means sp3d hybridization. 2 lone pair and 3 bond pair. That's why 3 then 2, that is 5. So sp3. Similarly, IF5, that is iodine will be here Out of 7, 5 electrons share with 5 fluorine, the remaining one lone pair. So its shape is square pyramidal. Square pyramidal shape. Square pyramidal shape means iodine will be here. Here fluorine, 1 will be lone pair. This is hybridization will be 1, 2, 4, 5 and 6. 5 and another lone pair, that is sp3d2, and shape is square pyramidal. Square pyramidal shapes. Regarding IF7, it will be IF7 means having no lone pair only, so it will be just, you can say it is pentagon. That means all fluorine at the or corner of pentagon. And so shape is, we can say it is 7. 5, then another 7, here 7. So it is pentagonal bipyramidal. Bipyramidal. Pentagonal bipyramidal. That means hybridization is here totally how much? 3, 7. 7 means it is hybridization is sp3d3. sp3d3. 4, 3, 5. sp3d, sp3d2, sp3d3. So you can say it is 1, 2, 3, 4, 5, 6, 7. So 7 1 pentagonal bipyramid, that is sp3d3 hybridization. So this is regarding the shape of different interhalogen compounds. Sometimes the Cn minus compound is also called pseudohalogens, pseudohalides. It is also called pseudohalides, because just like X minus, Cn minus, Nc minus is called pseudohalides, and Cn whole 2, if write Cn whole 2, this is called pseudohalogen. Pseudohalogen, just like X2. So these are some important that preparation and some structures of compounds of halogen, mainly oxides and interhalogen compounds and oxoacids of halogen. Okay, thank you.